We are continuing the discussion for the introduction chapter, and now we will take a look at or examine something very important, which is the CPU time. The CPU time is an important metric for our course here because it tells me if a machine is faster than a machine. So the CPU time, very critical to compute it the right way. Okay, so the question is how to compute CPU time. And let's give an example. And with this example, we'll see how we can compute that CPU time. Okay, suppose I have, for example, a program. And this program consists of, let's say, I have a load word, add, da, 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 subtract, and then let's say store more. This is a program of four instructions. Okay, we have a program of four instructions, and I need to find out what is the what is the CPU time. So let's say, for example, I'm going to draw here the clock signal, which is an important signal in my system. Okay, and that's so I can compute the, so this is my clock signal. Okay, anytime I deal with time, I have to think about the clock. And let's say, for example, here I have the very first instruction here, which is the load, is executed at the very first cycle. And let's assume, for example, every cycle time, we'll call it, or period, is 1 nanosecond. And also, let's assume every instruction, the instruction takes, every instruction takes, oops, sorry, uh, requires, let's say, instruction require one cycle. Okay. So in this, so this add the load instruction comes here and it is executed in the very first cycle. So this is one cycle, will take 1 nanosecond of the microprocessor to execute the very first instruction. Now we will go to the next instruction, okay, which is the add. So the add comes in here and we need to execute it in the next cycle, which is right here. Okay, another 1 nanosecond. So 2 nanoseconds to execute the first and second instructions. Okay, let's think about the third instruction here. Okay, let's the third instruction, which is the subtract. So the subtract comes in here and it is executed during the third cycle. Okay, so the third cycle here is another 1 nanosecond. And let's now do the last instruction, which is the store instruction comes in here and executed in the in 1 nanosecond in the fourth cycle. So you can see how many cycles I have. Well, this is first cycle, second cycle, third cycle, fourth cycle. I needed 4 cycles to execute this program. Okay, so what's the total time to execute the entire program? So this program needs from here all the way to here, okay, and the total time is 4 nanoseconds, and it needed 4 cycles, cycle 1, 2, 3, 4. So in terms of CPU time, I need 4 nanoseconds. It turned out there is a formula which allows me to express this in a much simpler way. So let's take a look at this formula here. Okay, so let's take a look at this formula and we'll see express this formula as the following. The CPU time, okay, let's say use a black color here. The CPU time, oops, okay, the CPU time is expressed as equal to instruction count. In this example, instruction count is how many? 1, 2, 3, 4 instructions. Okay, instruction count times what? times in cycles per instruction. So in this case, in my example, I'm assuming every instruction requires one cycle. Times what? Times the cycle time. Okay, so let's apply this to our example. Let's apply this to in my example. How many instructions? So in my example, how many instructions? Well, I have 4 instructions. Okay, well, every instruction requires how many cycles? It requires one cycle, so 4 times 1. Now, what's the cycle time? What's the period of the clock? It is 1 nanosecond equals 4 nanoseconds, which I have already computed. Okay, so again, the CPU time is what? Is expressed as instruction counts. How many instructions I have in my program. Now, times what? Times the cycles per instructions. We refer to this, by the way, as CPI. That every instruction requires how many cycles? In my example, one cycle. Okay, one cycle times the cycle time, which is 1 nanosecond. Okay, and by the way, if we use another window here, let's see. Let's express this one more time. Okay, so you can see here, we said what? We said that the CPU. Whoops, that's not what I wanted to do. Okay, the CPU, the CPU time equals what? We said it is instruction count, meaning how many instructions. So the unit for this, instructions, oh sorry, let's write this the right way. Instructions per program that are existing in my program times CPI. Okay, what's the unit for the CPI? They are cycles per instruction. Okay, times what? Times the cycle time, which is what? Which is second per cycle. These are the units. Now, what am I trying to measure here? I'm trying to measure the CPU time, which is how many seconds my program requires. Now watch how the units will cancel very nicely. Notice how the instructions cancels the instructions, cycles cancel the cycles, and then I am left with what? Seconds per program, which is what I am measuring per the CPU time. Okay? So this is one thing. The other thing is that what I can do is that I can combine terms in this CPU time to create different variation of this formula. Like what? I can combine these two terms. Okay, so if I combine them, what happens? Well, if I combine these two terms, and okay, let's just use a different color here. If I combine these two terms becomes what? They become the number of cycles. If we multiply the instruction count times the CPI, they are the number of cycles times cycle time. That also provides for me CPU time. So don't let anybody fool you by expressing or re-expressing this rule in a different way. It's the same thing. All what we did, we merged these two terms in one thing called number of cycles in the program. Now, I can also merge these two terms. And in this case, what I have is instruction instruction time. If I merge these two terms, instruction time. So in this case, CPU time equals what? CPU time equals number of instructions or instruction count times instruction time. Okay, that would provide for me CPU time. So what I want to say is that I can merge with this formula here. I can merge terms in a different way to get variation of the formula, but all of them, they provide the CPU time. Also, recall that cycle time equals 1 over frequency. Okay, or they refer to it sometimes as clock rate. Okay, all right. With this said, let's go back to the textbook here or the slides. Let's go back to the slides here, and we this is what we were discussing just a second ago. CPU time equals number of cycles, right? Okay, and see if I have an earlier slides here. Okay, number of cycles. Now notice that he times cycle time. Notice that he merged here two terms from the earlier formula that we talked about. What are these two terms? Instruction count times cycles per instruction, CPI. Okay, so don't be fooled by the variation of this formula. It is the same. We are just regrouping the terms in different ways, but at the end we are measuring CPU time. Okay, let's take an example. He said that we have a computer with this frequency, computer A, with this clock rate frequency, and CPU time of 10 seconds CPU time. Designing computer B, we aim for 6 seconds CPU time, so the CPU time equals 6 seconds. Can do faster, but causes 1.25 clock cycles. Okay, so this is the increase in number of clock cycles. All right. So he says, how fast must computer be? Okay, so he's asking about the frequency for computer B. Okay, so you can see that computer B we apply the formula. Okay, for the CPU time equals the clock cycle divided by the clock rate for computer B. All right, but we rearrange the term. We said the frequency or the clock rate equals clock cycles times divide by CPU time for the computer B. That is 1.2 clock cycles for which is for A, divide by 6 seconds, because this is the aim, 6 seconds. Okay, why 1.2? Because he said that number of cycles increased by 1.2. Now that what that means is that now I have expressed the clock rate in terms of the clock per cycle for clock cycles for computer A. Let's go to computer A. The clock cycles equals the CPU time times the clock rate. This is for computer B. I'm sorry, for computer A. Okay, all right, the clock cycles equals CPU times the clock rate. He told me that the CPU time is what, 10 seconds. That's coming from here, 10 seconds. And he told me that it is 2 gigahertz, right? And that provides for me, this is the number of the clock cycles. Now, I go back here to this formula and I plug in what I found out in terms of the clock cycles for computer A. So now you can see clock cycle for computer B. Now I can continue now. 1.2 times the clock cycle for computer A, which I just found, divide by 6 seconds, and turned out to be 4 gigahertz. So that is the frequency for computer B, so that it will be as fast for as computer A. Okay, all right. Let's go for another example. Okay, so here is now he says that this is the formula that we will use. Okay, which is CPU time, instruction count times cycles per instructions times the clock cycle. Now you can take the clock cycle down in the denominator and it becomes clock rate. Okay, now he says we have another example. We have two computers, computer A and computer B. The cycle time for computer A is 250 picoseconds, and the CPI is 2 cycles per instruction. And for computer B, the cycle time is 500 picoseconds, and CPI is 1.2. And he's asking me to find out which computer is faster. Okay, so let's compute the CPU time for A, instruction count times CPI times cycle time. Now, he told me that they have the same architecture. That means the instruction count is equal for the two computers. So the instruction count, okay, times the CPI, this is for computer A, all right, times the cycle, okay, so that gives me 500 picoseconds times I. Let's go for computer B here. Apply the same formula. Okay, instruction count, which is I, times 1.2, okay, CPI, all right, okay, which is coming from here, okay, times the cycle time, which is 500 picosecond. That gives me I times 600 picoseconds. So computer A CPU time is I times 500 picoseconds. I don't care about I because it will cancel when I compare the two of them. And for computer B, it's 600 picoseconds times I. And obviously, computer A is faster. Okay, how fast is computer A? We divide CPU time for computer B, divide by CPU time for computer A to measure the performance improvement in computer A, which is 600 picoseconds times I, divide by 500 picoseconds times I, and that comes out to be a ratio of 1.2. So that is how much computer A is faster compared with computer B. Okay, all right. Now, sometimes the CPI. Let's go back to our to our here our menu here, or our whiteboard. Sorry, here. Okay. Sometimes the CPI is not straightforward. For example, sometimes the CPI is not given a clean. So we say that the CPU time equals instruction count times CPI times cycle time. Okay, and we have said very simple in the previous example. We said assume that every instruction is one cycle it takes to execute every instruction. Well, that's very simplistic, and that doesn't exist in the real world. Well, so let's take an example which reflects the real world. So for example, let's have a program here. Okay, I have a program of 100 instructions. Okay, and let's say, for example, I have the loads. The load. There are 35 instructions, and I have an add, and I have 20 instructions of those, and I have a subtract, and I have 20 of those instructions, and I have 20 store. Okay, store, and I have a 25 of those. Suppose now, and this is the important, that every instruction of those has a different CPI. So let's take a look at the CPI. So this is the CPI. This is the count for every instruction. So suppose, for example, the load has a CPI of 2. The add has a CPI of 1. The subtract has a CPI of 1. And the store has a CPI of 2. Then the question, so this is my program, I have 100 instructions. So then the question, how can I apply CPI here in my CPU time formula? Answer, we have to find out average CPI, which is an average. So how do I calculate this? The average CPI in this program is as follows. We take every instruction. So now, out of out of the entire program, I have 35 out of the 100 instructions that they are load. Okay, and these loads have 2 cycles per instructions. Then I add this to, out of the instructions that I have here, let's change color here. Out of the 100 instructions, I have 20 adds, and those take 1 cycle. And then out of the 100, I have 20 subtract, and they are 1 cycle. And then out of the 100, I have 25 instructions, Yeah, this has to be divided by 100, by the way, over 100, and they are 2 cycles. Notice what I'm doing? I'm averaging. Okay, so I'm multiplying the CPI by the ratio. The CPI by the ratio of this instruction, the CPI by the ratio of this instruction, the CPI by the ratio of this instruction. Add all of this instruction and it becomes to 1.6. So this is the average CPI, which I can use in my formula up here. So let's go back to the textbook and continue our example. Okay, so let's go back to the slides and continue where we left off. Um, okay, all right. Okay, here's an example of weighted CPI. Let's read this example. We have 3 instructions. He calls them in the example, instruction A, B, C. Instruction A has a CPI of 1. Instruction B has a CPI of 2. Instruction C has a CPI of 3. Now, I have 2 programs. He calls the program sequence here. So program 1 has 2 instructions of class A and 1 instruction of class B and 2 instructions of class C. And program 2 has 4 instructions of class A, 1 instructions of class B, and 1 instruction of class C. Now, we need to compute the average CPI. Now, how many instructions I have? I have for program 1, okay, for program 1, we have 2 plus 1 plus 2 instructions, that is 5 instructions. That's the instruction count. Now I compute the average CPI since I have one. Let me just change the color here if I can. Let's see. Let's use. Yep, let's use the green. Okay, so I have one instruction here. One instruction. Okay. This instruction of a CPI 1, and I have 2 of them. Okay, all right, and I divide the 2 over the 5. Why 5? Because the number of instructions is 5. Then I have a CPI of 2 from class B, where I have a the okay, so I have 2 instructions. I have 2 instructions of class B and the CPI of 1, so I divide 1 over 5. Okay, let me restate this again. I have a CPI of 2 of class B, and there is 1 instruction out of 5. And then for this program, I have instruction class C where it has a CPI of 3. There are 2 instructions out of the 5 instructions. Then I do the math, and then my average CPI is 2. Similarly, program 2 will do the same thing. For class A, I have 4 of the 6 instructions. Excuse me. And for class B, I have 1 of the 6 instructions, and for class C, I have 1 of the 6 instructions, and I can compute the average CPI. Okay, all right. Okay, now next. Okay, so here is our main formula here. The CPU time. The CPU time is equal to what? Well, it measures what? It measures really second or per program. How many seconds I need per program? So how do you compute it? This is instruction count multiplied by CPI multiplied by the cycle time. Notice the units. The units will work very systematically. Instruction count is instructions per program. CPI, cycles per instruction, so I can cancel this by cancel this, and then the cycle time, seconds per cycle, can cycle by cycle, and then I end up with seconds per program, which is the CPU time. Okay, so you see how this formula of CPU time is very powerful, very powerful. It has three things. One, the instruction count, which relates to our instruction set architecture. Second, the CPI, which relates to the architecture and design of the CPU. And finally, the cycle time, which relates to the CPU design and the circuit design. It spans the algorithm, the compiler, the instruction set architecture. Very powerful formula. Very powerful formula. Okay. All right. Now, next. Okay, we're going to skip power here, and because we covered the power in other courses, so I'm not going to in greater depth here. So we'll take a look at and so is the cost of the die. Let's take a look at the CPU benchmark. What are benchmark? Benchmark are a benchmark is a collection of programs used to measure the performance of the CPU. So let's say, for example, here I need to measure the latest CPU from Intel, and so I have a let's say let's say 2020, and it's a collection of programs. Let's say I have three programs: program one, program two, program three, and then I run it on the Intel CPU, and I get in the first run I have 1 second, and in the second run, I have let's say for example, uh, 3 seconds, and in the for the third program, I have 4 seconds. Okay, so these are the performance. So how I measure the final performance, and obviously these programs, they were created very carefully to measure the performance of the CPU. So they have all the kind of difficult stuff and tricks to kind of stress the architecture of the CPU. So I have different numbers in these, but the spec, which is the benchmark, consists of these three. How can I get the final numbers? So the final number is computed by this formula, meaning in this case, what do? I multiply 1 times 3 times 4, then I raise it to the power third, sorry. Why power third? Because I have three programs. Okay, so I multiply them. So when this is referred to as the geometric mean, and typically used to measure these types of performance ratios, and give weighted and fair average number. This is in contrast with the arithmetic averaging, or arithmetic mean, where you add the numbers and you divide by their numbers. So if I were to do this in arithmetic mean, I'll say 1 plus 3 plus 4 over, because since there are three of them, over 3. That's the arithmetic mean. But that's not good for such averaging. So we use the geometric mean. So these are the benchmark used to measure the performance. There's a collection of programs to measure the performance of a CPU and compare them with other CPUs. Okay, now Amdahl's law is one of those laws that help kind of improve the CPU performance. Let's take an example for Amdahl's law. Suppose let's go. Suppose see if I go back to my whiteboard. Okay, here's my whiteboard. Okay, let's see. Let's see. See. Okay, here's my whiteboard. Suppose, for example, I have a suppose, for example, I have a collection of a program. Okay, and this program, let's say, for example, a I have uh, let's say, for example, these instructions that are math instructions. Math instructions: add, multiply, divide, etc. And then I have the rest of instructions: load and store. Okay, now so I said I have an idea to improve the performance of this program. So this is a program, okay? We run it on our CPU and we say we get, let's say, for example, 10 nanoseconds. This 10 nanoseconds is split as follows. We spend about eight nanoseconds on math instructions and 2 nanoseconds on loads and stores. Then I have an idea. I'll say, well, okay, what's the idea? Well, the idea, what we'll do is that we'll take these math instructions and run them on a faster coprocessor CPU, such that we can improve by 5 times the executions. Okay, so how will be the new time? So what will be the 10 nanoseconds now? What would be? Well, for a starter, we are not changing these 2 nanoseconds for load and store. So they stay the same, 2 nanoseconds. Okay, all right. Now, um, well, how about the 8 nanoseconds? With the 8 nanoseconds, they will be reduced to by 5, because I am going to run it on the improved mode, okay, which is the coprocessor. Now, if we do the math here, okay, so now you can see that what I have done is that I have created this improved mode, which has improved on the execution of the math instructions. Okay, all right. So now this is 1.6 nanosecond, and this stays the same as 2 nanoseconds. So what's the total here? The total is 3.6 nanoseconds. Okay, so from 10 nanoseconds, right? I improved the system by 10 to 3.6 nanoseconds. Okay, well, how about those 2 nanoseconds here? How about these 2 nanoseconds? Well, they are not impacted because I am not improving. I am improving the time for just the math instructions. Okay, so let's go back now to the slide and say, okay, what is Amdahl's law says? Amdahl said that the time which is we improved in our example 1.6 nanos, I'm sorry, 3.6 nanosecond, okay, is equal the time which is affected, which is the 8 nanoseconds, our example, divide by the improvement factor, which is the 5, plus the unaffected, the load and store, which is the 2 nanoseconds. And that gave me what? 3.6 nanoseconds. That's what Amdahl's law. Let's read it. He says the performance improvement to be gained from using faster mode, which is this one here, is limited by the fraction of time, of course, because this is the t affected. It's I cannot impact this. I cannot improve the unaffected by the fraction of the time the faster mode can be used. Okay, so that's what Amdahl's law states. Finally, the MIPS metric, it used to be one of the old metrics that they used performance, and the people they used to say, well, this machine is 3 MIPS or 4 MIPS. And what MIPS stands for is million of instructions per second. And if you express it in this law, it's instruction count divided by execution time times 6, because that's million instructions per second. But if we really simplify it, we'll see it's nothing but clock rate divided by CPI times 10 to the power 6. What's the problem here of this metric? Well, it is missing the instruction count. We say that the CPU time consists of 3 things multiplied by each other: instruction count, the CPI, and the cycle time. Well, I can see the CPI, the cycle time, which is the clock rate here. I can see the CPI, but I don't see the instruction count, and therefore that this metric is questionable because it missed one of the components, which is key to measure the CPU time, and that's why it is inaccurate. Okay, all right. So I think with that we conclude the discussion of the introduction chapter for the computer organization course. Thank you.